So thank you very much for the introduction. I am Javier Segovia, and I work here at IRI, and this presentation is about learning action models, which I think is a very interesting topic. I think it's very relevant to the AI field, and we have like few showcases also in robotics, and it's also about not just learning how to interact, but also how is the representation of the world. And we will show some systems, how they work, and we will show also some examples here at TD. So first, I would like to introduce myself a little bit about me. I did a bachelor in telecommunications engineering at UPF. Then I went to a company, Indra, and I worked there as a subprogrammer and so developer. But I decided to go back again to the university for doing a PhD in artificial intelligence. So I first did a master in intelligent interactive systems, and then I decided to go forth with a PhD in information technology and communications, but actually it's artificial intelligence. In my last year there, I also did a short stay in the University of Melbourne for 3 months as a visitor researcher. Yeah, very nice group in artificial intelligence there. And after that, I started at TD, that is this mixed center between CSIC and UPC, as a postdoctoral researcher in AI and robotics. Right now, I'm in a project in Horizon 2020 project that is called Imagine, where we want to disassemble electronic devices automatically. And we thought that this topic of learning action models is a very interesting showcase for this project too, because it's a very intuitive way to show what a robot can or cannot do. But we are still working on that. A little bit about my publications. I mostly publish in AI in the most relevant journals, in the Artificial Intelligence Journal, the Journal of Artificial Intelligence and Research, and also the top-tier conferences like ISCAI, IIII, or ICAPS. As I've been reviewer for these journals, for all these conferences, for a couple or 3 years, and I got a couple of awards also in science. One was in 2016, where I won the Best Paper Award of ISCAI. That is one of the larger conferences in AI. And the second was about my dissertation that was awarded by the European Association of Artificial Intelligence in 2018 with the Best Dissertation Award of Europe in AI. So these are the goals of this session. I want to mention that if you have any question, do not hesitate to ask me. So just write something, or I don't mind if you interrupt the presentation. So feel free. These are the goals of this session. I think because it's a topic that is not so close maybe to others related to robotics, I would like first to introduce a little bit what is the concept of planning, a formalization of the kind of planning that we do, that is classical planning. What is also introduce a little bit the language that is used, or in the language that we express the problems. That is the planning domain definition language, or PDDL. There are many versions of this language, but we are going to introduce the most basic one. And also, we will talk about what is this kind of problem of learning action models and why it's important. And we will review the most important systems in the field, like the state-of-the-art systems in the last 15 years. Furthermore, we will introduce also the problem of action discovery. That is a problem that we have been working here in IRI for a year, and how these systems can use interaction between. So this is the presentation outline to achieve these goals that are these 5 topics, like introduction to classical planning, this problem, the most popular systems, the action discovery, and intuitive programming, open challenges, and future work. So starting with the introduction to classical planning, what is planning? Okay, so we have an agent, we have a world. I think you are pretty familiar with this picture. And what an agent does is just acting and observing and acting and observing iteratively. So then an agent may think, what should I do? So what should be my next action? And Plato will say, think, then act. So this is what is planning about. You have to think, you have to reason about the world, the possible outcomes, the future goals that you want to achieve in order to select what is the best next action to apply in this world. So if we go back to the roots of planning, maybe the first paper that we find with what we understand right now as planning is this general problem solving by Herbert Simon, J.C. Shaw, and Allen Newell in '59, where they created a computer program to understand the information processes that underlie the human intellectual, adaptive, and creative abilities. So what they wanted to create is a kind of program where they can imitate somehow the human thinking process. And this was intended to work as a universal problem solver, which means, like humans, give me any problem that you want, and I will show you what is the solution to this problem. Related to planning will be, tell me what is the sequence of action that you have to apply in your world to achieve your goals. So how are the problems expressed, at least in this paper, were logical formulae that consist of sources or axioms, which mean your initial situation, and things or desired conclusions, which are the goals that you want to achieve in your problem or with your agent. And maybe the most important thing is that this was the first computer program which separated the knowledge of problems, the input, what we understand as input rules, from the problem-solving strategy, the way that we solve this problem. That is called the generic solver machine. So nowadays, this is what we understand as domain-independent automated planning. The general picture of domain-independent automated planning is that, where we have these 3 steps. In the first step, we have the input, where we specify on the one hand, the problem domain with all the rules that are all the actions that we can use to interact with the world. And on the other hand, we have the problem instance, the initial state and the goal condition that are separated, but both are used as the input to the planner. As you may think, this problem domain is fixed, so we can change the problem instance as many times as we want. We can pose as any problems as we want and keep the same problem domain, and the planner will give a solution. So this is what we understand as domain-independent planning. Give me any domain and any problem for that domain, and I will solve it. I will plan. So once we have this input, we have a generic solver, or what is understood as a planner that does search, does reasoning over this input, and generates this solution or plan that is the sequence of actions to apply, or the sequence of rules, or whatever, that maps this initial state to the goal condition. So here we have an example. This is the typical example in planning that is called blocks wall. In blocks wall, we have a gripper, we have blocks, and we have a table. So the idea in blocks wall is that we have any arranging of blocks in a scenario, and we want to map this setting to another setting by picking and placing blocks in this scenario. So this in this we can apply like many different actions, and it's a very realistic problem that we may find in many different industries of picking and placing objects in some parts of of the industry and moving to the other side. So these are the problem domain rules that we may find in this domain, like the way that we can interact with this world. We have these 4 actions of pickup, put down. Well, one does the opposite of the other. Also unstack and stack, that also does the opposite of the other. In pickup, if you can see clearly the image, we have the gripper with the arm that is empty, and the consequence of applying a pickup over the green block is that the green block then is being grasped by the gripper, and the put down does the opposite. So we have this green block on the gripper, and putting down means that you put the block onto the table. In the unstack, it's quite similar to the 2 actions above, but there is a subtle difference. That means that we pick up a block, but we are picking this block from a stack. This means that you have blocks below. If you have blocks below, you have to consider which blocks do I have below. So for this reason, both actions are the same, but one applies to the blocks that are on the table, and the other one applies to the blocks that are onto other blocks. And this is called what looks like a blocks wall instance, where we have this initial state, the source, and the goal condition. In the initial state, we have this arranging of blocks here, where we have 3 towers of blocks and the gripper that is empty. And the goal condition will be to have this specific tower, arranging the colors in this figure. And the goal condition is to have the arm empty. So a solution to this problem will look like this. We have this initial state where the blocks are in this setting, and we have these 6 actions that are being applied over these blocks and reach this goal state. The first action will be, okay, pick up the green block that is onto the table and stack this green block onto the yellow one. Then we will have the gripper empty again. So we can unstack the red block that is on the pink one and stack this red block that we have on the gripper onto the green that is already placed. And the last 2 moves will be, okay, then pick up the pink block that is onto the table and stack this pink block onto the red one that we just placed on the top of the tower. And with these 6 actions, we will map this initial state to this goal state. So how do we achieve this? With the planner, with the generic solver, where we have this starting node that is the initial state, and then we have all the possible different actions that we can apply over this environment. If we have this initial state, there are 3 possible actions that we can apply. That is unstacking the yellow block, picking up the green block, or unstacking the red block. But because we want to achieve first to place the green block on top of the yellow, we will follow the column in the middle. And then we will expand this node, and we will stack this green block onto the tower that onto the leftmost tower. But there is also another chance that maybe we leave this block on the same place, or maybe we stack this block on the tower on the rightmost tower. So if you see something like this is a tree search, and there are many algorithms that can explore this tree search. Let's say the most basic one that are like pretty old, like breadth first search, depth first search, or best first search, and there are others that are more novel, not so now, but like A*, and recently others that use heuristics like FF or FD llama, or iterated with, in this case, exploiting the structure of the state. There are like a bunch of algorithms, a bunch of heuristics that can be used to explore in this space. So what are then the planning paradigms? We have this agent that interacts with the world and observe. And what is an action about? An action may be the unique source of a change, which means that if we apply the action and the action has some effects, the only thing that will change the environment will be the effects of that action. So if I pick up a block, there is no possible failure. And I know that I will pick up this block, and the consequence will be that this block will be in my gripper. But there could be also exogenous effects, which means that there are some variables that we are not considering in our problem and may change the effects of our actions or the state, the consequence state. Also, actions may be deterministic or stochastic, that is quite different from the previous one, which means that I can consider that if I want to pick up a block, maybe my action fails. If my action never fails, it's deterministic in its effects. But if the action may fail, and I consider which is the possible outcomes, what are the possible failures, then this is stochastic. And another thing is the time. So an action can be instantaneous, which means that if I pick up a block, there's no time. So that the next state, exactly the next state, is that I have already the block grasp, which obviously is a simplification of reality in order to reason. It's an abstraction over time. Or also we can reason about the duration of the actions. Actions may be durative, and this is what is understood as temporal planning. Another thing is the observations. So once we have these settings of actions, we can observe, okay. And what are the possible observations? Observations can be full or can be partial, which means that if we have states, we can see the whole state and we can reason about all the possible state variables, or state variables are observable. Or maybe some of these variables are hidden, which means that we have only partial information about the state. Also, we can have noise in the state, or maybe it's noise-free, which means that if we apply an action, imagine that we apply an action that is deterministic, and we know what will be the effect. We observe that the effect is not what we predicted, which is impossible if it's deterministic. This means that we have some noise in the observations then. And also, the last thing to consider is like, do we have a goal-oriented agent? Does the agent has a goal, a specific goal? Or does the agent maybe just want to maximize an expected reward? Imagine that states bring some reward, like, okay, you perfectly grasp something. Maybe we want just to keep improving the grasping process, and we want to maximize this expected reward. While the goal condition will be maybe just grasp the object once you have achieved the grasping process, you have finished with your task. So what is classical planning about? Classical planning is maybe the most simple planning paradigm, which is that actions are the unique source of change. They are deterministic, they are instantaneous, they are full, they are observations are full, are noise-free, and we have a goal condition. Okay, but even that the planning paradigm is the most simple one, the state space, so the search, is exponentially grow. So we have state spaces that are impossible to visit. So we need some wise mechanisms in order to achieve these goals, because the graphs that are generated with these problems are possible to visit. So we have to look through the correct paths that to reach the goals. So are exponential. So if someone knows about a little bit about complexity, it's proven that is p-space complete. So what is the formal definition then of classical planning? We define classical planning as a classical planning problem as a four-tuple, F-A-I-J, where F is the set of fluents or Boolean variables, which also we understand them as facts, which describe a state space S with the size of 2 to the power of F, to the size of F. This means that we may have all possible combinations of Boolean variables, true, false values assigned to these variables. Each state in this state space is fully defined if the size of the state is the same as the size of the fluents, which means that all fluents or Boolean variables have either assigned true or false. If we have partial observation, the size of the state space will be lower than the size of the fluents that we have in our problem. A is the set of actions, actually the set of grounded actions. We will show an example of what grounded means, where each action consists of preconditions that are the list of the logical formulas that are over specified over the set of fluents. Imagine that we want to pick up the block. This means that we need our gripper to be empty. If the gripper is not empty and is already holding a block, we cannot pick up anything else. And then we have a set of positive effects that are Boolean variables that are set to true, and a set of negative effects that are the Boolean variables that are set to false after applying the action. In the case of picking up a positive variable that is assigned to true will be the holding. We are holding a specific block, and a negative variable will be that the gripper is no longer empty. And then we have the problem, that is the initial state, which is fully defined, which means that all variables in the state are either true or false. And the goal condition, which is a partial definition of the state, which means that maybe we just want to achieve some specific Boolean variables to true or false in the problem, which is the set of fluents and the set of actions is what we understand as the domain, or first order logic domain in this case, because we use predicates that are relations between objects. But F and A are grounded with the problem. We will show the example. And what is the problem? The problem is exactly the initial state and the goal condition where the objects are included, like the number of blocks, their color, their relations, and whatever we need. So how are all these things specified? Problems and domains are specified in the planning domain definition language, or PDDL. We have like multiple versions depending on each planning paradigm, but a basic recipe. But they are a basic recipe for classical planning. And for the problem domain, which are the rules, we have these three components: the domain name, the list of predicates that are all relations between the objects, and the list of actions that we can apply in the world that are conditions and effects over these predicates that we have above. And then we have a problem instance, which is a specific problem for that domain, which consists of a problem name, a domain name, which is the domain of the problem, or the list of actions that can be applied in this problem, the list of specific objects that we are going to relate, the initial state, which is the conjunction of grounded predicates, and the goal, that is the conjunction of grounded predicates. So if we use this formulation from before, from the classical planning problem, F-A-I-J, F will be generated between combining the list of predicates and the list of objects. The actions will be combined between the list of actions that we have and the list of objects. And then we will have the initial state and the goal that are already considering grounded predicates. So how does look like blocks wall domain in PDDL? So we show before the images of the actions, but how are they spread in this language? So we say that first we have this domain name. So we say that domain is blocks wall. In every problem, we have some requirements that are useful for state-of-the-art planners. In this case, strips, which is the most basic, that is just predicate logic. And we have this list of predicates for the problem. That is, we have we may have a block on top of another one that is below. We may have a block on table. We may have a block that is clear, which means that it has nothing above. We may have hand empty, where the hand empty means the hand of the gripper, or holding some block, which means that the gripper is holding one of the blocks of our problem. Then an action, we show just one example of an action in this domain, which is in stack. In stack, we have two parameters. We have top and we have below, which are two possible blocks, the block on the top and the block on below. Which are the preconditions to apply a stack? We say that we have a tower where we have two or more blocks, and we want to pick up the topmost block. To pick up the topmost block means that the top block must be clear. The top block must be on top of another block that it has below. And the hand of the gripper must be empty, so hand empty. If these conditions hold for specific objects, then stack then can be applied. Which are the effects, the consequences of applying a stack? So the topmost block will no longer be clear. This block won't be on top of the below, and the gripper won't be empty. And the positive effects will be that the block that we have below on the tower will be clear, and that the top block will be held by the gripper. In the same way, we can specify the other three actions: the stack, the pickup, and the put down. So how does a blocks wall instance looks like? So we have these three objects. Imagine a blocks wall with three blocks, B1, B2, B3. And we have this initial state where block B3 is clear, that is on top of B2, that is on top of B1, and B1 is on table, and we have the gripper empty. And the goal is to turn upside down this tower, to have the block B1 clear, that is on top of B2, and that is on top of B3, B3 is on table, and the gripper is empty. So if we have again this problem, this original problem, we have this set of grounded predicates that I told you before that we are going to explain what grounded means, which are, if you can see here, all predicates on top below, and here the list of objects B1, B2, B3. The grounded predicates are all possible combinations of objects with all predicates that we have in our domain. So we have the 6 combinations of having a block on top of another one, the 3 combinations of having the blocks on table, the 3 combinations of having the clears, the holdings, and the hand empty. And the same applies to actions. We have grounded actions, and we have 4 possible actions, and for each possible action, we have all combinations of their parameters. We have these 6 combinations for a stack, 6 combinations for a stack, 3 combinations for pickup, and 3 more for put down. And this is the introduction to classical planning, and it's very relevant because the problem of learning action models that we are going to introduce builds on top of classical planning. So, and let's pose this problem. We have now a new situation. and we want to encode a new domain as the one we show for Bloxwork. And we have someone, an expert, that says, let's encode a new domain. But typical users of computers, they are not experts. They are not programmers. They cannot they cannot pick a language and say, okay, I understand everything. I will encode a new problem and solve it. But maybe they want to program something like we program a clock alarm. So what they say is, I am not expert. I cannot do it. So then the expert says, okay, then we should change this paradigm of how we generate this domain knowledge, because so far the domain knowledge is created by experts. But this knowledge can be learned. And what is the general picture? That we change a little bit the problem. Instead of the plan be the solution of our problem, like in classical planning, like in the planning paradigm, we have the plan as part of our input. Also, our problem instance, where we have this initial state and this goal condition. All this can be used as input to a solver, and the solver, the idea of the solver is that we'll produce this problem domain, this set of rules that apply to the plan that you provided, but still guarantees that you can go from this initial state to this goal condition. So what is the exact definition of learning action models? It is a problem of learning abstract actions from an action execution observations, such that agents can reason about the dynamics of the environment and achieve new goals. So if we want agents to be autonomous and reason about their environment, they will have somehow to learn which are the possible actions that can be applied in their world. And this cannot be provided by experts, because at some point, if we have autonomous agents, they will have to learn by themselves which are the possible actions to apply. So an agent may think, what can I do from all possible actions? So observe and learn. Then you could think, which are the three elements of this problem? First, we have a hypothesis space, where we have all the bunch of possible domains with all possible actions in each. And one important thing to mention is that if we are considering more complex planning paradigms, which are also named more expressive, like algebraic expressions, this will increase the space of hypotheses, and the hypothesis space will be larger. So we may have, for instance, a domain that is blue, another domain that is pink, or other two, a combination of both, or whatever. So we have to reason about what is the exact domain that I have to learn for this problem. How do I learn? With input examples. Which are input examples? As we said, we have plans, and plans are a sequence of interleaved sequence of observations and actions. So we have states which are observed, apply an action, a state, action, state, action, state. Okay? But this is the most easier case. We have more complex ones where states may be noisy, states may be partial, states may be hidden, actions may be partial also, actions may be hidden. Maybe we know the length of the plan. Maybe we don't know anything about the length of the plan, and we just know few actions, few states. So we have all possible combinations that we will show now. And the third is the error function that is related to posterior probabilities. So maybe we think that our domain already is consistent with the input examples, and we are happy with that. But the error function will say, hey, maybe you are consistent with your input examples, but you can do it better. So you keep improving over your domains, and then you say, okay, success. You have the minimize an error or maximize a reward. Perfect. So going back again to the same planning paradigm, which is the hypothesis space that we use? So as we are using strips, which is the most basic language of sublanguage of PDDL, we will use the same features: a unique source of change, deterministic, instantaneous, full, noise-free, and goal condition. These are on the top, the action effects are related to action effects, below are related to observed states, and the goal condition is the terminal condition of a problem. But beyond the planning paradigm, we have three more features to consider that are, we can be either learners or observers. In learners, you interact with the world while you learn. In observers, you observe an agent, how it interacts with this world. We can also be system or object-centric, which means that we maybe want to learn the dynamics of the world by the actions that we can apply, or maybe we want to reason about the possible objects, how objects evolve through their possible states. A glass that is empty, a glass that is half, a glass that is full of water. So maybe we can reason about different states of the objects. And also we can reason about learning atomic actions, which means that we cannot have simpler actions than that, or maybe macro actions, which involve a sequence of actions that, like a pick and place, for instance. We can consider a pick as one, a place as another, like atomic actions, but maybe we could learn directly the macro action of pick and place. So again, we will focus on these ones. We are learners, we are system-centric, that we want to learn the actions, and we are atomic. We want to learn the atomic actions that to interact with the world. So what is the exact definition then of the hypothesis space? An hypothesis space is an action, what we understand as an action signature. An action signature is just the name of an action, like pick, and the params, a block. And the alphabet, which is sigma, or logic formulae that are all conjunctions of clauses. We have these triplets then now in the problem of action signature, precondition or effect, and phi, where phi is a predicate or its negation defined in terms of the action signature parameters. We will show an example now. Then an action model is a schematic representation of a planning action, like the planning actions we showed previously in the PDDL for Unstack, which consist of a name, parameters, a logic, formulas, preconditions, and effects. So we would just want to learn this planning action. And what is the hypothesis space? So this is denoted as H, where it is a set of all possible action models that can be defined over an alphabet sigma, that is defined with all the possible combinations of positives or negative predicates in my world. So let's put an example in Bloxball again. We have the Unstack, the action signature for Unstack will be the name, where we have Unstack, and the set of parameters, which is T and B, referred to top and below. Then we have all this list of possible preconditions, all these triplets of preconditions related to alpha, where alpha is the action signature, and all these triplets of effects related to alpha. In the preconditions, then we select these ones. The hand empty, the T is on top of V, and T must be clear. And in the effects, we select these ones. The gripper is no longer empty, the top is no longer on top of the block below, and the top is not clear anymore. And the block below will be clear, and the block on top will be held by the gripper. So once we have selected these triplets for that action, we can say that our action model will look like this one in the PDDL, where we have an Unstack, top below, and all these preconditions and effects related to these parameters. The second one, so this was the hypothesis space. The second one, that is the input examples. So we have this interleaved sequence of states and actions. which are represented by the interaction between the agent and the environment. And the agent may behave randomly, like I'm randomly exploring my world, or is goal-oriented, which means that you have a goal condition where you finish your exploration. So in the input examples, we have two things. We have state observations and action observations. State observations may be symbolic, full observable, and noise-free, which is the perfect case, and will look like this in the problem posed before for blocks, where we have a tower that is sorted from top to down as B3, B2, B1, and the hand is empty. Also, it could be the case that the problem is not specified in PDDL strips, and maybe we use something that is not symbolic and relational data. So states might be just nodes of a tree without any information about the predicates that are acting as black boxes. Or maybe states may be an image and transitions between images, which is what we could observe. Also, the full observability, it's like an ideal case, but maybe we have partial observability. Imagine that we have a camera on the gripper and we look just to the block on top. So we will see that the block 3 is clear and that we have the hand empty, but nothing else. And also can be noisy. Imagine that we see the whole tower, but we change 2 blocks in our observation. So these are the possible paradigms for the state observations. And for action observations, we have this unstack, this example of full observable noise-free, then stack of a specific block from another block. Partial observability will be just the label or the action name, like we are unstacking something, but we don't know what. Or noisy, like we are picking up B3 while we don't know that below there is another block. So input examples then are trajectory observations, where a trajectory is an interleaved sequence of possible empty states and action observations, like in this example that we see here. What is the exact definition then for a learning example? It is a set of trajectory observations. So as the one that we introduced was just an example of a trajectory observation. So instead of one, we may have multiple of them, where states and actions may be unobservable in each one of these trajectories. Note that each observation serves as an hypothesis validator, which means that once we learn an action model, we want to be consistent with the set of observations that we have. And some information from this list, such as the list of action signatures, could be inferred and used as background knowledge. So maybe we know that we have 4 actions in our domain, that they have these names, they have specific parameters that refer to blocks. So all this information that we have in a plan or that we have in a problem can be used as background knowledge for the learner. And an learning example here, for the problem of putting all blocks down on table for the same problem of having this tower of 3 blocks, will be to unstack one, unstack the one on top and put it down, unstack the next one and put it down, and we reach our goal state. So a learning example will look like this. And the last one is the error function, where we have these learned models and these observations, and we want to assess how likely is this set of models to produce these observed trajectories. So we have this error model can be based on data, it can be based on the structure of our models. In data, we will check something like coverage metrics, like that we cover the observations, counting errors, like how many preconditions are not met during the execution of our models, or redundant effects that do not include irrelevant information, cost of fixing a trajectory, in example, how the cost of removing or adding some state variables, likelihood functions. Or on the other side, we have the structure, where we have the counting model, cost of fixing the model, complexity metrics. So what are the most popular first order systems? Now we will do a short review of the most popular systems, which are ARMS in 2007, for instance, was maybe the first that achieved some solutions for this problem with some relevance. Where the hypothesis space is the set of strip action models given the set of action signatures and state variables. The input examples are fully observable initial and goal states, fully observable actions, and possibly some intermediate states can be partially observed. And it counts errors. It counts how many preconditions are unsatisfied and how many effects are incorrect. And the way to do this is using a maxat solver and strip action models. We don't have time in this presentation to look through all the details of these systems, but if the slides are shared at some point, you have all the references in each one of them in case you want to check any of them. So, and in the same year, there is another paper related to a stochastic domain. So instead of learning strip action models, it learned action models with probabilistic effects by observing these triplets. And instead of using counting errors, it uses a metric of optimization. So you use an optimizer and learn the probabilistic rules of the domain. In SLAF, it was the first online approach to learn action models. And it learns a CNF formula, which is always consistent with the observations. So what it uses as an error function is the coverage metrics, and this problem can be solved with a SAT solver online. So every time that it has an observation, it updates the knowledge and produces a list of strip action models which are consistent with the CNF formula. Loken maybe is the most different one, which is object-centered. It's based on objects, as we explained before, and it uses logic inference. So it learns strip action models, but with finite state machines with sorts of objects, which are evolving through the observations. In 2010, where we have another paradigm that is for learning ADL action models, where ADLs means that we have existential and universal quantifiers, which are just quantifiers over the possible number of objects that we may have in our problem. This is an extension of ARMS. And another one that considers noise and incomplete observations is noise in 2012, that also measures coverage metrics, but it uses perceptrons with DNF kernels. I leave all these systems for you to explore mostly, and I leave just the list of them. And Aman in 2013 that considered that plant traces may be noisy. So one of the things that we consider is that the sequence of actions is always correct. But in this paper, they considered that the sequence of actions maybe is incorrect, are noisy observed. So they use a graphical model solver for this. Then in 2018, there is a paper that explores also this with a fitness evaluation and genetic algorithms to generate the same strip action models. And FAMA posed the problem quite different in a situation where the sequence, there is a long sequence between the initial state and the goal state. So they compute the problem as a classical planning problem, and they just have the initial and goal state, possibly some observations in the middle, but are not required. And they compute the learning action models that map this initial state into this goal state. And then in representation discovery, that is the last one, where the input is very different from the rest. The inputs are label graphs, are graphs where the states are black boxes, and relations are the action names that relates one action with another one. So they do sample over the hyperparameters of the state structure. So like how many predicates we have, the arities of these predicates, how many objects we may have in this problem. And they learn to be consistent with this input graph, with the coverage matrix. They can do it with a SAT solver and they produce this SAT action models. So how this all relates to EDI. In EDI, we have contributed with two problems. One is the action discovery, which means what if action signatures are unknown, which means that we don't have the name, we don't have the parameters of the actions, so we have no information about actions, we just can see states. So what it tells is then you should search in the different hypothesis spaces. You have to hypothesize over hypothesis. Let's pose the problem. We have this hypothesis space of strips action models and state variables. And we have this grid where we have an agent that is moving, and the aim is to visit all cells in the grid. We would like to learn some action like this one, like move and in the grid where the cells or places are adjacent one to the other. And the input examples will be something like this, where we have multiple traces or trajectories, where we have this initial state and these goal states. This can be posed as a search in the space of hyperparameters, where we say we have a certain number of actions, and each one of these actions have a specific arity. And we search over the most simple domains. As long as we are increasing the number of actions and parameters for these actions, we're increasing the complexity of the domain, and we want to keep a domain as simple as possible. So we search, we specify the problem as other learning action model solvers like FAMA, where they have the initial state and the goal condition and pose the problem as a classical problem. We use a classical planner for this. And every time that the classical planner fails, we continue the search in the space of hyperparameters. And when we reach a set of hyperparameters that is solved, then we reach to the final action, to the final model, which in this case is the agent that can move between two cells. And the second contribution that we have done at TD is it's about intuitive programming, where we have this agent interacting in the world, but all they can do are picks and places of objects. So come with me, little Padawan. I will show you what to do with these picks and places. Let's pose this problem again. So we have, I guess that you have already watched this video before. So here we have a problem where caregiver sets the patient's mental and physical impairment and the robot's initial behavior. And then the robot assists to the patient while he is playing cognitive exercises, okay? But this set of cognitive exercises is fixed. And every time that they want to play something different, you have to call to a company, hey, program this robot to play this new game, and so that I can assess new metrics or new evaluations with my patients. So the same board that the patients use to play games can be used to teach new games too. So that's the idea. We have this human-robot interaction using an electronic board. We have this initial state. We have a person that is interacting with this board and is moving tokens in this board to reach a goal state. A move, for instance, of a pick and place macro action will be something like this, moving the 19th to the first position on the leftmost top. And the sequence of pick and place is a trajectory observation. So if we see these 5 moves, this is a trajectory observation. So an example is a not ascending order exercise. And we here show 2 examples of this exercise, where we have the storage rows of the rows where the tokens start, and the goal row where we place each one of the tokens. So in the beginning, we have all the actions which are discretized by the token and the time step where this token is being moved. And they consider all possible preconditions. And every time that you apply a move, because we want to be consistent with this move, we have to remove some of the preconditions. We have to relax somehow the action. And this is the kind of output that we obtain, something similar to PDDL. So you can move the token 19th in time step 1 from this location to this other location. And this the cell of from must contain this token, and the cell of 2 must be empty, like this. So the action signatures of picking and place actions are discretized, as I said, by token and timestamp. The effects of these actions has always the same pattern. It has always the same effect. Like something what is contained in the from is no longer in the from. And the from will be empty. The destination cell will no longer be empty and will contain the token that we are moving. So, and this will be the same for all possible macros we have. And then the preconditions is exactly the problem that we want to learn. That is the problem in learning the correct preconditions are the rules of the game. Preconditions are the key point of these exercises that they use for assessing the mild dementia patients. So here's a video of 1 minute that we use. Is an improved version of this problem. But as you may see, we have arrows. These arrows means what the system has learned. So first, there are no arrows because there's no knowledge, and as long as it's acquiring knowledge, more arrows appears, which are possible movements of tokens. And the idea is to move those tokens that has no arrows but still are valid, because this is giving more information to the system of what is an available move for this action, for this exercise. And as you can see, it's keeping learning, and the idea of this problem is to sort all tokens in ascending order. We did some hypotheses over 2 groups, and we detected that there is some improvement when we have feedback. And this is the output that we obtain for intuitive programming, that once we have the actions in PDDL style, you can translate this to natural language, like the destination to goal cell is this certain location. The source from contains this token. The destination is in, and so on. And you can use any kind of descriptive text to show these rules so that people that is not expert and interacting with a robot or a board can show how to learn these new actions. So this is the last point, that is to conclude. What are the open challenges now that we have in learning action models, so that we can learn hybrid action models? In example, right now we are just considering Boolean variables, but maybe we have integers or real estate variables or procedural preconditions like functions. Imagine that to apply an action, we want to check first a function of a program, and if this function of a program returns true, we will apply this action. If this function of a program returns false, we want to apply this action. So we can have like very complex action models that we are not considering. And in contrast, this will increase, this will make the problem more expressive and will make the hypothesis space larger. In this case, we have the Hanoi Tower, where we have 3 pegs and we want to move one disk to another place. So the preconditions to do a move from one peg to another one will be to a function that is calling to the size of the disk that is on top of a specific peg that is smaller than the destination peg. So as you can see, this is some kind of recursive information, which is much more complex than what the strips offers. And a second challenge will be the way that we collect examples. So we can explore the state space
And there are state spaces that we have states that are reversible. But if we break a glass of water, this is not reversible. This is a dead end. So we need some wise mechanisms to explore this state space, avoiding somehow these dead ends, or even recognizing these dead ends to prevent a robot or any agent to reach them. And also the exploration of an unknown state space. So if we don't know which is the state space, if we don't know which are the state variables, and we have to create it from observing images, pixels, sensors, or sensory data, this becomes much more complex. So this is like a very huge challenge. Also, realistic learning examples, as previously mentioned, that right now we have these plans, we have a lot of information, but to be more realistic, well, we should focus on sensory data samples at a certain frequency, like hidden Markov models that have been already successfully applied in this kind of problems. And this assumes that partial and possibly noisy observability and of states and actions. Like if we have this sequence of samples of temperature that is increasing, maybe we can infer that people in the room is also increasing, where people in the room maybe is a question, but it's not a state variable that is observable. And also in scalable algorithms for action model learning. Like in example, we have an online learning approach that satisfies some hard constraints, that optimize soft constraints, that scales in the number of examples, and scales in the number of action models, because there are like a huge limitation in the number of, in the size of hyperparameters that we consider. As more learning examples we provide, the worse it works. If we consider just hard constraints, then we are not optimizing something. If we optimize something, then we are not considering hard constraints. So combining all of them is a huge challenge too. And maybe one of the mechanisms that we can apply in these cases will be an online learning approach. So what is our future work here at IRI in this topic? So we are working now as learners, but we want to move to observers. We want to move to observe how agents that already know how this world works, like imitating a human interaction, can show these examples, these goal-oriented examples, and learn from that. If we can learn from this in an online fashion, then we can be the unique source of change, or we can detect also exogenous effects. We want to consider, at least now, deterministic and instantaneous actions, but we can also deal with full or partial observability and noise-free or noisy, as we said, of hidden Markov models before. So just summarizing the session, we have seen an introduction to classical planning, to classical planning and PDDL, that is a language. We have at least tried to understand the problem of learning action models and the most important features. Short review of the last 15 years in this topic that has been thoroughly explored, and our contributions to exploring these systems of learning action models when these action signatures are completely unknown, and how this can be used in assistive robotics when teaching robots from symbolic examples, like the interaction with an electronic board. There is also a list of open challenges, and our ongoing work is in the topic, and we think that is very relevant. This is a mandatory topic if we want to have autonomous systems that can learn from human examples. So no great discovery was ever made without a bot. Yes, Isaac Newton, thanks for your assistance, and if you have any question.
Thank you, Javier.
Thank you.
And any question for the attendants?
People got stuck in the middle.
Okay, it seems
No worries.
there is no questions.